This is AP Podcast 7.3, and we're going to talk about how you can calculate the pH of weak acids and weak bases. So really quickly, we're going to review how you calculate the pH of strong acids and bases. The first question we have says calculate the pH of a 0.1 molar nitric acid solution. Well, remember, what makes something strong is that it ionizes completely. So when we're looking at nitric acid, it's HNO3. We know it's going to break up into hydrogen ions and nitrate ions. And if this was originally 0.1 molar, the concentrations of these two ions right here that are produced are also going to be 0.1 molar. And that's kind of, if you think about the mole to mole ratio, for every one of these we produce one of the hydrogen ions. For every one nitric acid we produce one of the nitrate ions. So this thing's concentration is going to match up with the hydrogen ions because it's a 1-to-1 ratio if we think about the ionization reaction. So what all I have to do then is just plug in my concentration of H plus into the pH calculation. And pH is equal to negative log of the H plus ion concentration. So in this case it's the negative log of 0.1. And when I do that I get an answer of 1. So there's your pH of that solution. This next one, it's the same thing. This is another strong acid. Remember, there's only 6 strong acids, so you need to memorize that list. This is a strong acid, so again, when I'm doing this, I can just say that the pH is equal to the negative log, this time of 1 times 10 to the negative 10th. And when I do that, I get an answer of 10. Really quickly, a couple things on significant figures. When you're calculating pH, this number right here has 2 significant figures. That leading 0 does not count. This trailing 0 does. So 2 significant figures in my original concentration. When you do your pH, significant figures only count for the decimal spots. So this 1 out in front here, or if it were a 2 or a 3, that does not count towards your significant figures. The significant figures are kind of reflected, I guess, in the number of decimal places that you put on your pH. So in this one, since there were 2 originally in the concentration, I put 2 on my pH. This one, there's only 1 significant figure, so that means I actually need to only have written 1 decimal place. That should have been 10.0, not 10.00. That would have been too many significant figures. All right, we have 54 milliliters of a 0.00125 molar nitric acid solution, and it's mixed with 25 milliliters of 0.025 molar hydrochloric acid. What is the pH of the resulting solution? Well, both of those acids are strong acids, so they're both going to contribute H plus into the solution, and they're going to add together. So what I'm going to have to do is I'm going to have to figure out how many moles of H plus come from this solution, how many moles of H plus come from the second acid, add them up and calculate my new molarity of H plus, because they're going to join together and it's going to affect the pH. So what I'm going to do is I'm going to start by calculating the number of moles from the first solution. So I'm starting with 0.054 liters. I changed that to liters. And then I just multiply it by the molarity because it's moles per liter. You can also just rearrange this in the molarity equation. Molarity equals moles per liter, and you can just solve for moles there. So this is equal to, when I multiply that out, 6.75 times 10 to the negative 5th moles. So my second solution is 0.025, nope. Oh yeah, that'll work out. It's 0.025 liters, and it's also 0.025 molar. So moles per liter, and when I do that calculation, it's 6.25 times 10 to the negative 4th moles. When I take those two numbers and I add them up, I get 6.925 times 10 to the negative 4th, and that is moles. And just like in our previous problems, because these are both your strong acids, the concentration that they give you is also equal to the H plus. So we didn't have to do any conversion from nitric acid as a whole to the individual H plus ions because they're directly related, because it's a strong acid. So this is 6.925 times 10 to the negative fourth moles of H plus. I need to add up the volumes because I need to put the new total volume on the bottom. So I have 25 plus 54 is 79 milliliters, but I need that to be in liters. So 0.079 liters. If I take those two numbers and I divide them, I end up with a concentration of H plus. That is now 0.00877 molar. Then I can just use the pH equation and plug it in. 0.00877. And when I do all of that, my pH of my solution is 2.057. And I carried it to 3 decimal places because in each of these numbers, nope, that number there's not. There are only 2 significant figures in some of these, so this should be rounded up to 2.06. And we should get rid of that 7 right there. So 2.06 is your resulting pH. All right, what is the pH of 25 milliliters of a 0.25 molar solution of NaOH? This is a strong base. So my NaOH, when I put it into solution, breaks completely up into sodium ions and hydroxide ions. This does not matter how many liters, milliliters, gallons, whatever. The volume of this doesn't matter. What matters is that, again, if I have 0.25 molar initially of this, I'm also going to end up with 0.25 molar sodium ions and 0.25 molar hydroxide ions. And this is what I'm going to focus on. What I can do is I can calculate the pOH first, because this is the hydroxide ions. I calculate the pOH. So negative log of 0.25. When I do that, I end up with 0.602. And then what I want to do is to find the pH. If I remember that the pH plus the pOH always add up to 14, then I can just subtract 14 minus 0.6 because this thing only has 2 significant figures, so I'll just drop that too. So 14 minus 0.60, and we're going to end up with a pH equal to 13.40. And that makes sense. We're dealing with a strong base, so we should have a relatively high pH. All right, that was the review of the pH of strong acids and strong bases. It's pretty simple math. You don't have to worry anything about equilibrium because they ionize completely. That is not the case with weak acids and weak bases, though. They do not ionize completely. Weak acids are given a Ka value. The A stands for acid, Kb for bases. Just like we were dealing with Ks in the chapter before this, it's an equilibrium type of reaction. So we make it a little different by saying Ka and Kb because we're dealing specifically with acids and bases. But it's going to be the same thing that we have done before. So ice tables again. A good relationship to remember is that the Ka times the Kb is always equal to the Kw. What this is if I'm talking about a weak acid's Ka times its conjugate base, its Kb of the conjugate base, will give you Kw, which is 1 times 10 to the negative 14th. So if you know one, you can find the other. So I have chlorous acid. Well, I could find the chlorite. I could figure out the chlorite ion. I could figure out what its Kb value is because I can use this expression right here. So if we know one, we can go conjugate acid base. We can figure out the other. So this question says, what is the pH of 25 milliliters of a 0.25 molar solution of acetic acid? And because they gave me a Ka and acetic acid is not on my list of strong acids, what I know is I'm going to have to do an equilibrium type of reaction. I'm going to have to deal with ice tables and equilibrium reaction expression. So the first thing I want to do is write out what happens with acetic acid. So acetic acid is HC2H3O2. And in order to make this maybe look a little better, I'm going to rearrange this. I'm not going to write it like that. I'm going to write it like this, CH3COOH. This H on the end, that's the acidic acid, the acidic proton. That's the one that's going to leave. We're dealing in equilibrium, so double-sided arrow. You're going to be left with the acetate ion and a hydrogen ion. So however much this ionizes, that's what it's going to ionize into. We better make that a plus. Okay, so the first thing I'm going to do is set up my ice table. I want to use concentrations just like I did before. So right now my volume doesn't matter. It says I had 0.25 molar originally, so 0.25 molar. And then before it ionizes, there is none of the acetate ion and there's none of the protons. The change here, I'm going to lose that and I'm going to gain these two. There are no coefficients, so it's just plus and minus x. So at equilibrium, this will be 0.25 minus x. This is just x and this is just x. I'm going to set up the Ka just like I would a K. So I'm going to do the concentration of the acetate ion times the hydrogen ion over the acetic acid's concentration. So when I take my equilibrium values and I plug them in, I end up with x times x on top, my two products, over 0.25 minus x. And when we are doing these weak acid and weak base pH calculations, you're going to ignore the minus x. Because these Kas and Kbs are so tiny, we're going to assume that whatever this change in x is not enough that's really going to matter if I exclude it from this minus x part right here. So in order to find x and to make my calculation life a little easier, I'm going to get rid of the minus x on the bottom and just make it 0.25. And we know from the Ka they gave us that all that is equal to 1.8 times 10 to the negative fifth. So when I take this thing and I rearrange and I solve for x, what I find out is that x is equal to, let's see, 0.00212 molar. Okay, so if x is 0.0021 molar, I look back up in my problem. This does not matter anymore to me. This does not matter anymore to me. What really matters is the H plus because we're trying to calculate the pH. So I know that the H plus concentration is equal to x, and x is equal to this. So that x is equal to my H plus concentration. All I have to do then is say that pH is equal to my negative log of the answer I just found. And when I punch that into the calculator, I end up with an answer of 2.674. And that is the pH of this solution. So we'd use the ice table for the equilibrium. We needed to figure out what are the equilibrium expressions. We used Ka to solve for x, and we ignored the minus x on the bottom to make our math lives a little easier. Found out what x was, and we plugged it in because x is equal to the H plus concentration. We plugged that answer into our pH formula. So the next question is, what is the percent dissociation of 0.325? Molar solution of, probably should have finished that question, of, it should say formic acid, and then formic acid's Ka is 1.8 times 10 to the negative fourth. Okay, so there's the completed question. So the percent dissociation, you take the amount that's dissociated on top, and you divide it by the initial concentration, and because it's a percentage, you're going to multiply by 100. So what we're going to do in this case is we're looking for x. Because x is what is going to be the amount that's dissociated, that's what we're going to put, and then the 0.325 is going to go on the bottom. So we're going to set up another ice table. Formic acid is HCOOH, and when it goes into the equilibrium reaction, you get H plus, and you get COOH. I probably should have written that a different way. Oh well, we'll go with that. Ice. So initially we have 0.325. After it dissociates, we're going to lose some of this. We're going to pick up some of this. So we're going to end up with 0.325 minus x, x, and x. And my Ka is going to be equal to my products, which is the x times the x, over the reactant, and I'm going to drop the minus x just like I did before. And all that's equal to 1.8 times 10 to the negative fourth. So I solve for x, and when I do all my math, I end up finding that it is 0.00765 molar. All right, that is x. That is the amount that is dissociated. So that number is going to go on top of the percent dissociation equation. I put the original molarity on the bottom, which is the 0.325, and I'm going to multiply by 100. When I do all of that, I end up with an answer that is 2.35% dissociation. So you can see that usually not even 5% of these acids will dissociate, the weak acids and the weak bases, which is why we're able to ignore the minus x because it follows that 5% rule. The Ka's are so small that it hardly dissociates at all. All right, the next question. Calculate the pH of a solution that contains 1 molar HCN and 5 molar HNO2. Also calculate the cyanide ion in the solution at equilibrium. So the first thing we're going to do though is we're going to worry about finding the pH. If you look back up into that table on that page and we want to find Ka's, I'm going to look for the Ka of HCN. The Ka of HCN is, let's look. Let's see, 6.2 times 10 to the negative 10th. And then if I look for nitrous acid, HNO2, I look for that one, and it is 4 times 10 to the negative fourth. There is a huge difference between this one and this one. This is still weak, but this is very, very, very weak. So what we're going to see, because there's a huge discrepancy, is that HCN, whatever H plus it produces, is going to be minimal in amount to this. So when I'm trying to calculate the pH here, I'm just going to ignore the HCN. It's not going to affect my pH because it's not going to add to the H plus ion concentration enough that the pH is going to change. So all I'm going to focus on for the pH is finding out what a 5 molar solution of nitrous acid would have for a pH. So HNO2 will go into H plus and the nitrite ion, our ice table here. We initially have 5 molar of this before it dissociates, 0 and 0, minus x plus x plus x, 5 minus x, x, and x. So again, Ka is equal to, for the HNO2, 4.0 times 10 to the negative fourth. That's equal to the products over the reactant. And I'm going to make my life easier, and I'm going to get rid of the minus x on the bottom. So it's just 5. When I do all of that information and plug it into the calculator and rearrange it, what I find is that x is equal to 0.0447 molar. So because x is 0.0447 molar, remember that is the H plus right here, so I can calculate pH, negative log of 0.044. When I do that, I get a pH of 1.35. And I probably should have another number on there, except I don't know what it is. So we're just going to go with that. You should have one more number because I have 3 significant figures in my concentrations. So add another number there, whatever it is. All right, that is the first part of the question. The second part of the question says, calculate the cyanide ion in the solution at equilibrium. Well, I'm going to have to erase this, but I need to remember some of this information. So we're going to clear the screen. Okay, I need to remember back to some of the numbers that I had on the other page. So HCN, its Ka was 6.2 times 10 to the negative 10th. And then the X, which we found, which was also equal to the hydrogen ion concentration, was 0.0477 molar. Those are 2 numbers I'm going to need in order to calculate the second part of this question. So if I write the equilibrium expression or reaction for HCN, it's going to break into H plus and Cn minus. I want to do my ice table. So originally the HCN is 1 molar. The H plus is not 0. The H plus is what came from the HNO2. And if we remember back, that's why I wrote this number up here. So the H plus is not 0 originally. It is going to be 0.0477 molar. The CN minus, however, will be 0. So what we wrote here is the expression that's saying before any of this dissociates, there's 1 molar of that. The H plus is already there from the HNO2, and there's still none of the CN minus. So still minus X, plus X, plus X, 1 minus X, 0.0477 plus X, and X. So what I'm going to do is set up my Ka so I can solve for this X, kind of my second X. So it is 0.0477 plus X times X over 1 minus X. Because I like to make my life easy and it's not going to matter, I'm going to get rid of the plus X and the minus X on the top and the bottom. And I'll rewrite this as 0.0477 times X over 1. And all of that is equal to the 6.2 times 10 to the negative 10th. So when I solve this thing for X, my new X, I am going to get, let's see, 1.4 times 10 to the negative 8th. That new X is this Cn minus ion concentration. That is what we were finding right here. So there's your final answer for that one. So when you're given a solution that has a mixture of acids or a mixture of bases, you want to compare Kas, or you want to look to see, is one a strong acid and one's a weak acid? If you have a strong acid and a weak acid, only the strong acid's going to matter when you're talking about pH. If you have a mixture of 2 weak acids, usually the one that has the higher Ka is the only one that matters. If they're awfully close, you may want to do both and kind of add it up and solve for your new concentration of H+. But normally when they give you a mixture, there's only one that's really going to contribute the H+, and that's the only one that matters when you're trying to calculate the pH. Okay, next question. What is the pH of a solution where 25 milliliters of 0.25 molar nitric acid is mixed with 25 milliliters of 0.25 nitrous acid? Well, nitric acid is a strong acid. That's strong. The nitrous acid over here is weak. So what that tells me, if I'm mixing a strong acid with a weak acid, the weak acid does not matter. The strong acid is going to be the only thing that's going to affect the pH. So this just becomes calculating the pH of a strong acid. All I'm going to do to calculate pH is take the negative log of the concentration of my strong acid, which in this case is 0.25 molar. So when I do that, I take the negative log of it, I'm going to get 0.60, and that's my answer for that question. Next one, what is the pH of a 0.25 molar solution of ammonia? And ammonia is a weak base. So this problem is a little different than the ones that we've done, which were weak acids. Now we're dealing with weak bases. They've given me the Kb. It's 1.8 times 10 to the negative 5th. So just like my weak acids, I'm going to write an equilibrium expression for my weak base. With weak bases, you have to include water. Because a base is something that accepts a proton, you've got to show where the proton's coming from, and in this case it's water. So I have ammonia and water. What's going to happen is the ammonia is going to take a hydrogen. So it's going to become ammonium, and it's going to be left with the hydroxide ion. So there's your expression for that. We do the ice table, and initially the ammonia I had 0.25. Water does not have a concentration, so it gets ignored in the ice table. It's just there. Here we're 0 and 0 before anything happens. So this is going to be minus X, and plus X. So we have 0.25 minus X, X, and X. What I'm going to do is use the Kb and solve for X. This is looking just like what we were doing with our acids. I have X times X, my products, over 0.25. I'm going to ignore this minus X just like I did before. All that needs to be equal to 1.8 times 10 to the negative 5th. When I do that, what I find is that X is equal to, let's see, 0.0021. So my answer right there is X. This time though, when I look back up in my expression, I see that X is no longer H plus, X is now OH minus. So this is the concentration also of my hydroxide ions. So what I'm going to do is I'm going to calculate POH first. So negative log of my X, and what I end up with is 2.68. Then to find the pH, I'm going to take 14 minus that, and my pH of this one is going to be 11.32. So difference between the weak acids and the weak bases. Weak bases include water in your expression, but you don't have to add it in, I guess. It's just there so you can see where the H comes from that goes and shifts to the base. Use the Kb, sulfur OH minus, and then you're going to find the POH, and then you're going to subtract from 14 to find the pH. All right, last question. Last question says, what is the pH of a mixture of 25 milliliters of 0.25 molar KOH and 25 milliliters of 0.25 molar whatever this is, CH3NH2? This is a weak acid, or I mean a weak base. This is, I think, methylamine. So this does not fall into the category of strong bases. A strong base are these guys that have the hydroxides on them. So strong base, weak base, this is a problem just like 1, 2 before where we had a weak acid and a strong acid mixing. The weak base is not going to affect the pH at all. So all I'm going to focus on is the strong base. Because it's a base, I'm going to calculate POH first. So POH is going to be the negative log of 0.25, which is 0.602. And then to get the pH, we subtract from 14. I'm just going to cut it off there. So this is going to be 13.40. So the pH is 13.4 for a strong base, which it should be because they have the higher pHs. Okay, that is it for the problems that we're going to do here on the podcast. We're going to do some more in class, but make sure that you can set up those ICE tables and use them in order to calculate the pH of weak acids and weak bases.